Welcome to my video tutorial on the Matlab program Chapter 3 turnpike.m from my book on public economics. Now this tutorial teaches you to write a program turnpike.m on the computation of the transition in an OLG model. This application is taken from my book Public Economics from chapter 3.34 on the dynamics of the command optimum, and it would be highly advisable that you have some prior knowledge of MATLAB. If not, perhaps you would like to start with chapter 3 OLG1.m from my other applications which you can download. This program is much simpler. Now, in the present case, I will first tell you about the economic problem, about the turnpike behavior. In the second part, we will go through the code of the Matlab program. The new material in this program is the solution of a nonlinear equations problem. And in the third part, we will look at an exercise. So I will give you an exercise and hope that we can go through it together. It might be advisable that you pause at this point and try to solve it yourself. So let's get to the material. On my slides, in particular on slide 50, you find the description of the dynamics in the command optimum. So we study a two-period overlapping generations model. We have a young and an old cohort. Period length is equal to 30 years, and we use a Cobb-Douglas production function with an elasticity of alpha equal to 0.36. Instantaneous utility is logarithmic, and the discount factor is equal to 0.4. So this amounts to assuming a discount rate equal to 3%, and a population growth rate is set to 10% over our 30-year period. So this amounts to an annual population growth rate of approximately 0.3%. The central planner applies equal weights to the utilities of the different generations, and we study the transition over 20 time periods. Now, for our parameterization, we get a steady state capital stock k equal to 7.40, and the initial and the terminal capital stocks k0 and k21 are chosen to be 70% of this steady state capital stock, so they are equal to 5.18. The dynamics of our command optimum are described by the equations 34a through 34c, which can be condensed into a nonlinear equation, a second order difference equation in the capital stock kt. So this equation 35 we would like to solve for initial value k0 and a final value k21, so a two-point boundary value problem. The solution is presented by the figure on slide 53. So we have hump-shaped dynamics of the capital stock over period 0 through 2021. Now, this behavior in the OLG model is interesting because it's a little different from the one that we know from the Ramsey model with a finite lifetime. So if we study the Ramsey model with a household who lives 22 periods, and has given initial capital stock 70% of the steady state and a final capital stock equal to 70% as well, his behavior looks different. So in period 0, in period 1, he starts to increase his capital stock much faster than in the OLG model, and gets close to the steady state capital stock, stays there, and returns to the final steady state capital stock only a couple of periods prior to period 21. So this behavior is named turnpike behavior because it looks a lot like you're traveling from one place to another. So assume you live in New York, in a suburb of New York, and you want to travel to a suburb in Philadelphia. What you do is you try to get to the motorway as fast as possible in New York, continue to travel on the motorway until till Philadelphia, and then get off to get to your final destination. So this is similar to the capital accumulation in the Ramsey model with finite horizon, and this is because it's been named turnpike behavior. Now in the OLG model, the adjustment is much slower, and we do not even get close to the steady state of 7.4. So our OLG model behaves much different than our Ramsey model. And this is important. Why? If you study welfare issues, welfare policy, and for example compare economic policy to increase pensions or not. Now in the case of the Ramsey model, the adjustment to the final steady state is much faster than in the overlapping generations model, and this may have important welfare implications because slower adjustments also mean that cohorts or generations may not benefit as fast as possible from, let's say, a policy that's Pareto efficient in the final steady state. So you may get a different welfare ordering of public policies in the case of an overlapping generations model, and you should use it if your demographic structure, of course, is important for the description of your economic problem. Now let's turn to the numerical problem to solve this second order difference equation. Essentially, we're looking for 20 unknowns, k1 to k20, using 20 equations. So equation 35 for t equal to 0, 1, 2, and so on up to t equal to 19, which gives us 20 equations as well. Now we can, however, make use of the recursive structure. So we have the value k0. Now let's assume we have a value k1. Then with the help of 35 we can compute k2. And with the help of k2 and k1 we can compute k3 and so on. And finally we can compute k21 with the help of k20 and k19 and compare our implied value of k21 with the exogenously given value of at period 21 and see if it's equal. And if it's equal, we are done. If not, we have to update our guess of k1. So we have essentially transformed the problem of finding 20 unknowns into a problem of finding one unknown. And the solution then looks like this. So let's go to the numerical problem, to the computer code. For this reason, download all my computer code for chapter 3 from my homepage and save them all in the same directory, otherwise it will not work. So please be careful with this. Now the problem that I would like you to open is chapter 3 turnpike.m, and first we should see if this works. So let it run and see if everything is fine on your computer. And as you can see, it computes the solution as graphed in the slides and in my book. So the problem works fine. Now in order to understand the program, it's good to debug it together. So let's set a breakpoint in line 18. For this, just move the cursor to line 18 on top of the minus sign and just use the left hand side of your mouse click to insert a breakpoint in line 18. And now we can run the program again. So this is basically the first line or entry line after we have explained in the header the name of the program, the author, and when this was written. We have cleared the working space in the memory, and now we define a structure par, including the parameters of this economic problem. So in the first step we introduce the parameter alpha equal to 0.36, and we go on with the discount factor beta equal to 0.4, the population growth rate 10%, and in line 21 we compute the steady state capital stock K. So this steady state capital stock is equal to 7.4. You can find out this by moving the cursor on top of the variable. In the next step, we set the initial and the final values of the capital stock in period 0 and in period 21, and we set the number of transition periods 20, so this is the number of unknown capital stock. We initialize the periods from 0 to 21. We initialize the vector of the capital stock with 22 zeros. And now we look at our nonlinear equation K-dyn and analyze its behavior. For this, please use the arrow step in so that we can compute this procedure, this function, and we have transferred our parameter vector par to this procedure with the values of alpha n, k0, k final, big T, and the value of k1 for which this recursive scheme of equation 35 is to be evaluated. So our value 7.4 for the steady state just as an example to run this procedure. So we use the values of alpha and n and initialize the vector with the capital stock from k0 to k21 with 22 zeros. The first entry is set equal to the initial capital stock, and we compute kt2 from 2, which is equal to our value k1, as our unknown x given by the calling function. And in the line 11 through 14 we do the iteration over the equation 25. So now we compute the third entry in the vector kt2, which is equal to k2 in our model. So in the vector, the next element k2 is 9.64 once k1 is given by 7.4, and the initial capital stock k0 is given by 518. This follows from equation 35. And now we can do the whole loop, but this is a little bit cumbersome to go through this computation 20 times. We jump to line 15, where all values of kt are computed, and look and compute the difference between our implied value of k21 with respect to the given value 5.7. And in our case, this difference is 29.76, which will be returned to our calling function here. So this is our value for the nonlinear equation 29.76, and now we try to find a solution so that this is equal to 0. Well, let's take an initial guess that the k1 is just 1% above k0, and provide this guess to the solution of our nonlinear equation. So if we want to solve a nonlinear equation, we need to provide first the function, which is k-dyn. We need to provide an initial guess, which is k-guess, and in front of the function we need the sign in Matlab, and in this brackets here we specify with regard to which of the two argument the nonlinear equation solver fsolve should search for a root. So now Matlab knows it has to find a value of k so that k-dyn is equal to 0 for given exogenous parameter par. The solution is transferred to the variable k-sol, so for k-solution. So let's compute this, and k-sol is equal to 5.34 in our case. Now let's go through the rest of the computation. We have given the value k0 and k1, and now we need to compute the remaining values k2, k3, and so on. Again with the recursion over the equation 35. So we get, for example, 5.48 as our next value. You can see there's a little inaccuracy. So we have a little imaginary part, that's the inaccuracy of this solution algorithm, of this nonlinear equations algorithm. And now we jump to line 46 where we graph the solution. Run to cursor in line 46. So we graph the solution, and clearly you can see here that our solution coincides with the one presented in the book and in my slides. So this concludes the second part of this tutorial. We have gone through the Matlab code to solve a nonlinear equation problem, in this case in one unknown variables. And you may now do a couple of exercises to get more expertise in the computation of nonlinear equations problems. One exercise would be to solve this problem backwardly. So in our approach we used the value of k1, so we could iterate forward up to the value of k21. Now we can do the opposite. We start at the end, k21, at the final period, and we provide k20. And with the help of the recursive equation we can then compute k19. And with the help of k20 and k19 we can then compute k18 and so on up to k0 and find out if our k0 is equal, or implied k0 is equal to the exogenously given k0. If this is the case, we have found a root. Now in order to do this, however, there's one additional complication. In equation 35, let's go to the PDF file here, to our slides. In equation 35, if you have k0 and k1, it's no problem to compute k2. If you have k2 and k1, if you want to compute from this with the help of equation 35 k0, you have to solve a nonlinear equation. So what you have to do in the routine KDUN is to solve a nonlinear equation problem within a nonlinear equations problem. So I would like you to set this up. We will do another exercise, and our exercise will be to study the original problem of finding the 20 unknowns k1 through k20 in 20 with the help of 20 equations, nonlinear equations, equation 35 for t equal to 0, 1, 2 up to 19, and find the solution for this more complex problem with 20 functions. Now, how do you proceed to solve such a problem, and which is building upon old code? Now, the first thing you do is, of course, to save your problem under a different name. So now we want to use to solve a multivariate problem with 20 unknowns. So why not name the new program chapter 3 turnpike multivariate? And you have, of course, also have to change this in the header and change the date when you for your program, for the version of your program. So this is May 23. What we need to do is, of course, now use a different recursive function. Let's call this function multivariate and save this function as kdun multivariate. Of course, all in the same directory. So this is our dynamic equation 35 in chapter 3.34, and now our value of x, our unknown, is the capital stock from periods 1 through 20 corresponding to the entries 2 to up to 21 in our local variable kt0. We also would like to compute 20 unknown variables, so we have to initialize a vector y with zeros. This will contain the solution, the 20 solutions of our nonlinear equation as provided by equation 35. And here again we do our iteration over these capital stocks here. So let's apply this as a temporary function and check that our new nonlinear equation is provided by this line. And of course we also have to, sorry I forgot, supply the parameter value for the capital stock in the last period, par.kFinal. Sorry. So what have we done? We have assigned the values from the unknown x to the capital stock to the variable kt2, and also assigned the initial and the final value. Then we have initialized our nonlinear equations, so 20 equations in the variables of the capital stock, and in line 16 and 17 we compute equations 35 for t equal to 0, 1 up to t equal 19, and we return simply the value y as the return from the function kduin multivariate. So this concludes the changes in the function kduin multivariate m. Save it and go back to chapter 3 turnpike multivariate and do the other changes which are necessary. So we erase equation 30 and need to provide a new guess for our 20 capital stocks. Now it's not a scalar, but now we have 20 entries into our column vector. So why not assume that they all equal, so that the capital stock stays constant from period 0 to 21, which is the easiest guess, of course. Then we can compute the solution. We have to change the function name here. And we have to, well, then we are done. And we have to change line 36 and the following. So the solution now, ksol, is kt2 of 2 up to par big T plus 1. And of course kt2 of par big T plus 2. So in period 21, corresponding to the entry 22 in the vector kt0, is equal to par kFinal. And we can erase this recursion and plot the figure again. So let's save it, run it, and see if it works. Well, clearly we have made a mistake here, so let's see where's our mistake. For this, let's go to the equation here and check with the book if we have done everything accordingly. And Of course, we have forgotten to subtract kt of I, kt2 of I. Sorry for this, but this teaches you a valuable lesson. Usually it never works in the first place, so you have to make adjustments while you compute your solution. So let's check if this was indeed the mistake. No, not yet. Go back to this. All right, temp. Check this equation again. Sorry for this little interruption here. Go through the equation. So kt plus 1 plus kt plus 1 to the power alpha divided by 1 over n minus 1 plus alpha kt plus 1 to the power alpha minus 1 over 1 plus n squared times temp. Now here comes temp minus kt plus 2. So this now should be it. Sorry for this. Now let's run again. And again there's a mistake. I'm dreadfully sorry. I forgot to introduce y of I. I'm sorry for this. Okay, I'm sorry for this little delay, and we have solved the problem, and thank you for being so patient with me. So let's go back to our home base. So what we have done now, we have done our exercise, completed our exercise. As you can see, sometimes there are little problems that are annoying and you have to dig a little deeper to find out where's the problem. We have finished the computation of the transition dynamics. If you have any problems, please do not hesitate to contact me, send me an email, and I will try to help you as soon as possible. Thank you.